my full-time job is actually working on calibration. So I know that's everyone's dream. Everyone loves any calibration problem when it shows up. So yeah, we're all really excited to be here. So turning the dial on automatic calibration, I guess to kind of give some context, there's a degree of autonomy in sort of all of the things that we do in robotics, and there's often times where manual intervention or some sort of, engineering intervention is required to sort of continue or move forward with what we kind of have as our ultimate goal, which is shipping a product that does something. And so when we're talking about calibration, we're kind of talking about a first step where sometimes you don't always have all of the information you need to know, and you have a very ambiguous problem, especially early in the phase of a robot, where you may not know exactly the full scope of the work that you're going to need to do by the time you're at the end of the project. And so in terms of autonomy and calibration, I specifically want to talk about kind of two ways that I see people kind of think about calibration today, and maybe try to invert or change some of that thinking. So the initial way that I think people are kind of used to calibration is sort of this sort of offline or manual approach, right? We're waving checkerboards around. We might be post-processing data. That could be a ROS bag or an MCAP or a DB3. But really what it is it's this sort of envisioned process where it's manual, it's one sensor at a time or one sensor system at a time, whether you do cameras first and then your LiDAR, and then you kind of tack on your IMU. And this kind of lends itself to calibrating infrequently. And that's because this process is painful, as I'm sure the raucous applause was sort of implying earlier. But basically, this idea of offline or manual calibration is kind of put in direct contrast with what we often see being called online or automatic calibration. And this online or automatic calibration, the idea is, we take our checkerboards and we get them out of here, right? Throw them in the trash. Don't ever look at them again. We're not going to post-process data. We want to hook into a network. We want to do live, real-time streaming. We want to be able to kind of get these things on the fly. We're calibrating all of our sensors all at once and all the time. And there's sort of a big valley in the middle of this that kind of we look at calibration, and it's either you kind of have this really janky, difficult process where you've got to train people to use checkerboards and move them and dance the right way, or you have something that's kind of perfect and has solved all of your perception needs already. And what I've kind of learned in my experience at Tangram and helping lots of different companies and robots at different stages in the company too, is that middle valley is actually the most interesting part of autonomy, or at least I think it is. Because if we kind of go with sort of the framing approach that I've shown here, we're just really making a bad analogy for what calibration should be. In particular, we're kind of saying calibration's a light switch. It's either entirely solved and I'll never think about it again, or it's entirely not solved and it's always going to be a headache. And the reality is that we can't treat such an important part of the process as something that's either done and never thought about, or undone and always going to cripple the business. So I wanted to come up with a better analogy, and that's sort of the title of this presentation, is Turning the Dial on Calibration. Specifically, I want to talk about turning dials in calibration and sort of some of the steps that we can take to move from that, painful manual calibration world and start to get closer to automatic calibration, but even perhaps not even getting there if we find ourselves at a happier medium. And so for that, I have sort of distilled this down into a handful of dials that we might be able to look at and explore when you're thinking about calibration at your company and for the kind of product or sensors that you're using. And so that's product requirements, the operating environments, engineering controls is a really important one, and finally what I call process legibility. But sort of the broader overarching theme of what I want to cover today is treating calibration at your company as an operation and not just a one-off or a one-time expense. Calibration is something that you're probably going to end up thinking about whether you like to or not. Obviously, I love thinking about calibration. It's all I do every day. But for many of us who are developing things, there needs to be sort of a broader sense of how does this tie back into the business, and how do we get calibration under control and get the reins on it? So let's start by talking about product requirements. Oftentimes when I'm asked to sort of engage with a new customer, they want to use our calibration software at Tangram. I'm coming into this not knowing very much at all about what their robot is. I might know they have 2 cameras and an IMU, or 2 cameras and a LiDAR, but sort of the way in which I'm going to be able to influence both the data capture process for calibration, or perhaps the level of autonomy we can achieve using a combination of our product and best practices, is going to depend on what the product is for and what we want to do with it. So in particular, I've got 2 examples here of like a delivery robot and sort of these task robots, these arms that are doing some kind of cooking or food prep. There's a big disparity here between like the numbers and types of sensors that you might see in a product, and you might also have a vastly different model for onboard compute or how these things are wired together. You may not have the same sort of energy specifications, and this kind of influences the degree to which, 1, autonomy is required, and 2, whether it's possible. In particular, if you have a delivery robot like this one shown here, the Marble, what you might find is that if you want to calibrate continuously all the time, you're going to need lots of sensors and lots of compute, which means you're wasting battery, which means you have a lot more weight that isn't doing the thing that's important. And so if you were to take that same example and try to pack it onto a drone, we might not be able to make that work, because a drone is going to have weight requirements and energy requirements that are going to be vastly different. And so from the outset of a project, when I come in to look into how to automate calibration better, I'm specifically looking at sort of things like this. What is the intended application, and how does calibration fit into that story? The last one here, we're going to touch on a little bit, but I'm going to come back to this near the end of my presentation, and that's certification. We talk about autonomous vehicles, self-driving cars, these sorts of things. The certification process is actually very difficult for a lot of the software being developed for this. And so how you structure your calibration, how often you recalibrate, what metrics you use to sort of manage that, all comes back to, like, can this be running on the thing in real time? And so when we think about autonomy, we have to get away from just talking about autonomy in terms of this is a service or a ROS node just running in the background, and move towards a world where we think about how does this fit into the certification process? How do we validate these things? And so on that same topic, let's talk about another thing that kind of affects sort of the thinking around autonomy when we enter into that kind of discussion with a new customer for the first time, and that's the operating environment. In terms of the operating environment, is autonomy possible is really a question that we have to ask ourselves. And for rigid static sensor arrays, for example, those little robot arms doing some cooking, we might not need as frequent calibration. It may be that we have fewer sensors, and sort of the environment under which they operate doesn't actually affect their intrinsics or their extrinsics in a material way over longer periods of time. If you want to contrast that directly to autonomous vehicles, vibration from operation may just induce a requirement that recalibration is like way more frequent. If you are driving on a road and you have 2 big sensor arrays mounted on your mirrors or on the edges of your hood, and they're constantly shaking like this as you go down a windy highway, eventually that's not going to be physically the same as it was when you were calibrating in a factory. And so that's where more autonomous options like getting rid of the checkerboard but still doing this semi-infrequently at stops, or capturing data to do validation and just flagging that a vehicle must go back for calibration, or just flagging that an incident has occurred, is often a way to achieve sort of the same end result of what autonomy would have, is that we are not putting unsafe robots into the field, but at a much cheaper cost. We don't have to have something that's constantly running all the time. converse that with the fact that autonomous vehicles do have large batteries, we can oftentimes run some of these processes alongside the actual navigation and vision stacks that are being run today. Okay, so I've been taking a bit of a dump on these, checkerboards and marker boards, and that's a little bit disheartening because, we all love our checkerboards. We all have a favorite one. I know everyone here has an Aruco tag that they pin up on their bed at night. But this really comes back to what I like to think of as engineering controls. When we're designing a process for calibration, we really have to think about what is the control on the actual solution space. It's this big multivariate optimization, and what we're going to end up sort of running into is that if you don't have any engineering controls, you're purely relying on the sensor data. And so more autonomous calibration is sort of the removal of these exterior engineering controls and these interventions, whether it be having people in the field or waving a checkerboard or even having signalized targets whatsoever, and relying specifically on the sensor data. And so there's a trade-off between the number of minimum sensors you might need in order to be able to do some degree of autonomy, directly contrasted with how many other exterior engineering controls you have. A famous problem in sort of vision is that a single camera can't really tell scale. You have what's like the dollhouse problem, where if you take a photo of a house, you could have a perfect recreation of that photo as a dollhouse, and sort of geometrically and mathematically, your camera doesn't know what to do with that. If it's calibrated, it does. But solving that problem is not possible if you don't have more sensors to give you more information. And so especially when we look at customers and we have experience where customers don't have the ability to add more sensors, drone companies, anyone with a sort of smaller size package, or where additional sensors just wouldn't make sense. Like on a robot arm, do you really need 5 cameras to, detect objects in the bin? Just not the case. And so fully autonomous calibration really comes down to a requirement where your interior engineering controls, the number of sensors you have, how they're oriented, how their views overlap, how you combine that data, both in terms of the geometrics and mathematics, need to be managed in order to get a successful calibration. And this directly leads into my last point on process legibility. Process legibility is this idea that we are able to kind of read into our process. We know what we're doing, we know why things went wrong, we know how to interpret the results. And so when we make a calibration, these are almost entirely evaluated on a set of heuristics or metrics or predefined acceptance criteria that we have somehow produced. And so exterior engineering controls, like a checkerboard, provide an easy way for us to produce legible accuracy and precision metrics. The most obvious one is reprojection error. If we know something about the geometry of the board, we know something about our cameras, it's very easy for us to produce a reprojection error statistic or a metric and to understand, did calibration even work? And this is a question where oftentimes, folks come to us at Tangram and they say, we have these calibrations, we recalibrate frequently, but it's kind of a gamble, 50-50, if the calibration we just did is going to work, and we kind of want to know that in advance. And so by having sort of process legibility, which is something that we really cared about in our product, we are able to produce accuracy and precision metrics that make it easier to make these decisions. And sometimes when you lose those engineering controls, you're also losing those legible metrics. And you're putting yourself in a position where you're trusting heuristics that aren't as easy to interpret and can sometimes lead you astray. And so sort of the bigger message here is that in order to get a more automated calibration process, we have to consider the trade-off of what metrics can we compute and what metrics do we need to compute in order to make some decisions about, is this calibration accepted? Do we want to use this? Can we move forward? And so just to give a brief example here, this is an example of like some of the metric output from our software, and how that will show reprojection errors. And this is notably different than what you might be able to get if you were working in the field. All the same, because this is Actuate, we want to look at visualizations like something like Foxglove or perhaps Rerun. And we want to be able to look at these things both while they're happening in real time, but it's also possible that we want to look visually at what's going on post after an incident has occurred or after something has gone wrong with our calibration and we're just not sure what it is yet. Both of these sort of qualitative and quantitative requirements are extremely useful in being able to have insight into the process and be able to design autonomous systems that we can actually trust and rely upon. Because it's one thing to sort of automate calibration so that you never notice it, but if you never notice it at the cost of many other errors, you've made sort of a false gain. So what can be done? I've listed sort of a kind of big encompassing tent of problems that kind of occur when you're moving between sort of this manual to autonomous calibration. But really what I want to get at is that calibration is an automation or is an operation. It's something that has to be continuously done in your company, something that has to be continuously managed. There aren't necessarily like one-stop shop platforms for this, but Tangram is trying to answer these questions and work with partners to be able to develop these things in the future. So, what constitutes a failure? How do you know when calibration is the problem? How do you know if a better calibration would have prevented something? How often do those failures occur? And what do we have to do in order to correct for it? There's a big difference between having sort of warehouse robotics, where at the end of, a robot's shift or when their battery is about to die, they go off in the corner, recalibrate themselves, sit on a charger, right? That's very autonomous. But that correction isn't the same level of intervention of, maybe I have an autonomous lawnmower in the field and now I'm asking an intern to drive out there with a checkerboard. That's not ideal. Nobody wants that. And so we have to consider both like what engineering controls do we want and what kind of labor considerations does that like put pressure on the business. Nobody wants to push a checkerboard out to the field because that's just too much work. And so kind of to conclude here, your calibration process may not be static. In particular, you might need to add new automation for target motion over time. You may need to either move from target-based calibration to target-less calibration, depending on the context. You may need to do a mixture of both. Reintroducing checkerboards down the line shouldn't be harder than taking them out. But oftentimes, like having these sorts of periodic validation processes can sometimes be difficult to compose into an existing software and evaluation pipeline. And so you need to reevaluate these as the project evolves. To end here, I've talked about several of these axes of calibration can be made more or less autonomous. We have considerations like engineering controls or data capture that can change depending on where we want to go from A to B. And Tangram works with customers today to be able to try and understand like the life cycle of your project as a whole and kind of how calibration would fit into that based on where you think failures would occur. And sort of my last greater point, sometimes manual checks are still necessary and sometimes more cost-effective. Validating calibration against a target is an easy example, but there's plenty of other examples where we have shown customers that a fully autonomous solution isn't desirable due to the additional compute, additional cost, and just sort of the overall complexity it bears on the organization. And that can obviously change over time. So thank you all very much. Think about that next time you're calibrating.